Okay, so here's an example device, and your device is probably going to be different than this, but no matter what it is, it's going to start out with some sort of potential energy. Potential is going to go to kinetic, and then from your kinetic, you can grab the velocity off of that and the direction of the velocity off of just the geometry of your device. And you'll take that and see what sort of targets you'll be hitting depending on that initial potential energy. So just by way of example, I'll walk through this one, but then you need to walk through your specific potential energies and kinetic energies for your device. Okay, so here we have this little wedge of cheese here. That's going to be what I launch, and these black lines, consider those to be springs. So this is a bungee cord, and we're going to stretch those bungee cords back to start with some sort of a potential energy, let it go, and then see how far our target does. So just what the constants that we're going to be using here, we'll have to figure out the position that our projectile leaves our device. So this is XP, YP. So this is just the position that we leave the device. We'll also define a target position. So XT, YT, this would be a target position. And the difference between these two, that's what we'll use our constant acceleration equations for projectile motion. We have a few dimensions here. So this is going to be 0.5 meter thick and 0.85 meters long. If you make two triangles out of each side of this, that'll get you how far the string is stretched. We'll also have friction that's slowing it down. So we have the distance we pull it back to. This is going to determine what our initial potential energy is. That's going to determine frictional losses. And some of these things will be kind of hard to measure. So getting an exact spring constant, what you can do is just, if you do use a bungee cord, just start hanging some weights from it. Measure change in position versus change in force. See if you can get that spring constant. It'll probably be a little bit off, but that's sort of our fudge factor, that we can change our spring constant a little bit. We can change our friction coefficient a little bit until you can actually get what you have in this Excel spreadsheet to match what you're physically creating. So you need to make your device, test it out, and see that your device matches what your spreadsheet is calculating. That's the real trick. And your friction coefficient and energy loss and things like your spring coefficient, those are the things you can play around with to get this thing to actually work. Okay, so here we are on that other spreadsheet and how I have this set up, and you're going to need to come in here and kind of modify a few things for your own device. But I've got a kind of a table at the top for all of the constants for the device. So I have the spring constant for the spring, the angle that my table is going to be aligned to. I've got friction coefficient for my little objects sliding around, and this could be frictional losses for rotating objects and just in the gears and any kind of little connection in here. And then for the rest of it, what I have is a giant energy balance. So we have our kinetic and potential energy at the starting position. We can throw in work, so energy lost due to friction. And then this is going to translate to the energy that it leaves our device with. And from the kinetic energy it leaves our device with, we'll grab the velocity off of that, split velocity into x and y components, and then we can calculate what target that will hit. So the goal of this is to just make some kind of a giant spreadsheet or a great graph that you could do something like, say, okay, if I stretch my elastic back this far, then I will hit a target at this X position if it's at this height, kind of a deal. And if you have a whole bunch of lines, then you'll be able to just grab your spreadsheet and hit any target that you want. You'll need to test this out because you won't quite know your frictional losses and some of those non-ideal factors until you actually test it out. So you'll probably want to actually build your device first, and then after it's built, get that ruler out, take measurements, start measuring things like your spring constant. You can measure spring constant by just adding a weight and seeing how much it deforms. So F equals KX. So just, fill a water bottle up and see how much that stretches out your bungee cord or whatever it is. So figure out a way to measure what kind of potential energies you're creating, and whether it's gravity or springs or whatever that potential energy is. Then also kinetic energies. If you have something rotating, don't forget to add in that moment of inertia for rotational motion. So not just 1/2 mv squared, but 1/2 I omega squared as well. So get all of the kinetic energies, all of the potential energies. The work, this is going to be your big fudge factor. So it's really hard to measure those frictional losses. But once you see the difference between your calculations and what it actually does, you'll be able to kind of calibrate your results by playing around with your friction coefficient for your work calculations. Okay, so the column that we're going to start out with, and there's a couple different calculations, rather than going from the target to the distance, we're actually going to just start with the distance, and trust me on this, the math is just easier to go this way. So what I have for this device is we're stretching the elastic back, and I'm going to see this little D equals question mark here. So I'm going to fill in a column that goes from 0 to 0.85 meters. This is actually a little bit large. I want your devices to stay within a 2 foot by 2 foot by 2 foot box. So we're talking about just a small tabletop device in here. We're going to be in a conference center, and it's a pretty nice conference center, but small device going between 2 feet to 12 feet. If you want to make something bigger, we can maybe go outside afterwards, but for the actual competition, small device that you can aim and hit a variety of targets with is what we're going with. Okay, so if we're going from 0 to 0.85, what kind of increments? I'm going to take some nice small increments, so 0.025. Okay, and then I'm just going to copy this down. If you grab the lower right-hand corner and just pull it down. Okay, so there's kind of stretching it from 0 to all the way back. From this initial stretch, what would my potential energy be? Okay, so let's go over to the next column here and figure out potential energy. Now there's going to be potential energy from the spring, and also a change in potential energy from the height of my little projectile. The spring is going to dominate, but let's put all of these columns in here and calculate all of it. Okay, walking through the PowerPoint that goes along with the spreadsheet, what we have, here's our energy balance equation. T is kinetic energy, V is all the potential energy, U is any kind of work, so frictional losses. This is going to go to our final kinetic and potential. For kinetic energy, we're going to have 1/2 mv squared, or if you have some kind of an arm flying around, you'll have to calculate your 1/2 I omega squared. Let me know if you have this, and I can send you some equations for moment of inertia and help you out. This is actually a little bit more into chapter 17, but I can help you through this piece of it if you have some kind of a rotating object here. Our potential energy, so this is mgh, 1/2 mv squared, any kind of a spring that you're using. Okay, and just, let me know if you're having trouble figuring out how to calculate this too. So remember, all of these potential energies come from the equation force through some kind of a distance. So let's say you have a mousetrap spring, and instead of some kind of a linear distance, you're rotating through some angle d theta. So in that case, dx is r d theta, and you would have force dr would be force r d theta. So you could look at how far through the rotational angle that goes, and then you can decide, is this a linear spring? Is this a non-linear spring? If you have, so there's a moment through an angle, force r d theta, or if it's straight line motion, it's just like, friction coefficient times normal force through a distance. So any kind, or mgh, any kind of force through a distance, that's going to go through your potential energies and to your frictional losses and work equation. So, kinetic energy, starting out, that's going to be 0. Potential energy starting out, for our situation, it's going to be both from gravity and from the springs. Let's do the gravity first. That's not too bad. So mgh. If we stretch it back some distance d, then the rest of this height is going to be the length of my device, 0.85 minus d. I'm going to have to fill in the angle that I have over here, and then there's my height for my starting mgh. So I have mg and h over here is equal to 0.85 minus distance sine of theta. Okay, so let's go ahead and put these two chunks in it. We'll put the initial kinetic energy, and we'll also put our initial potential energy in here. So here's our initial kinetic energy and initial potential energy. And you can study these equations on the PowerPoint. I'll go through it here in Excel as well. Okay, so here we are back over at our spreadsheet. So we're going to start with 0 kinetic energy. I guess we probably don't really need this column in here, but it's just good practice to keep track of everything in here. So just copying that down for the whole thing. Move those over to the side. And then if you remember what we're doing for our gravity, this is going to be equal to m, and for the weight, I'm going to copy this value down, but I don't want this cell to change, so you want to add dollar signs to this. If you have Windows, F4 adds dollar signs to it, and that just keeps that cell constant. So there's m, g, and then our h for this one ended up being 0.85 minus, and this is the distance we're stretching it back to, times sine of, and I have this angle up here calculated in radians. So again, I'm not going to type a number in here. I'm going to bring everything back to this top table so that later on I can change my angle and it will change all of my calculations for me. So this will be able, you can manipulate it. Okay, so there's my starting potential energy if I don't stretch the string back at all. And you can see that as I stretch it back farther and farther, I'm getting closer and closer to the ground. So my starting potential energy gets closer and closer to 0 as we stretch it back farther and farther and pull it closer and closer to the ground. Okay, so just walking through that PowerPoint presentation again. So now we have our starting kinetic energy, the potential from gravity. Next up will be potential from the springs. So if you remember what the springs are doing, we're looking at this yellow cord and we need to figure out the length of this cord. We have a column with the length that's stretched back to d, and this is just going to be an a squared plus b squared equals c squared kind of deal. So the length of our spring is half of the width of this. So if this is 0.5 meters, there's 0.25 meters squared, and the distance it's stretched back to. And we're going to need to take that length, subtract off the unstretched length of the spring, which I have as 0.2. So even at the very top, it'll still have a little bit of stretch in it. So there is the potential from the spring. And we're going to go ahead and take that and put that equation into here. Now, there's two sides to this, right? So instead of 1/2 kx squared, there's 2 of it, so that kind of negates our 1/2. But we'll have 2 times 1/2 k. For k, we're going to reach back up to where our spring constant was in the table. And then for our x squared, we have to calculate that from how far back we're stretched. Okay, so here we are back in the Excel spreadsheet, and we're going to now calculate the starting potential energy from stretching those spring backs. There's 2 springs, so we're going to say equals 2 times that 1/2 times K. So we have our spring constant up here at the top. I'm going to add dollar signs to that because we're holding it constant. 1/2 K, and then x squared is where it gets a little bit confusing. So x squared, this is going to be square root of this a squared plus b squared. So this is our distance squared. So there's the length of our spring minus the original unstretched piece of elastic. I'm going to grab that up here from my table as well. So there's the total length of that spring, and we have to square it. 1/2 K, and this whole thing is the stretch, and then we're squaring it. Hopefully that makes sense. Okay, so there's the initial stretch, and I'm going to double click on that. If you double click on the lower right hand corner, it'll copy that equation all the way down for you. So there is all of our starting energies. The last thing we have to add is our work. Okay, the next column we fill out here is for work. You'll notice that work is negative. It's slowing it down. What we have here is, let's say that this little block is scraping all the way up, right? So there's some distance, and we're just going to calculate a simple friction force. So we take our mg, split it into our normal and tangential components. This angle comes back up here, so the normal component, that's going to be the cosine theta piece of it. So here's our normal force. Friction force is just our friction coefficient times this, and then the work is going to be our force times the distance. And the distance is going to, again, be this distance we're stretching everything back to. So now you're starting to see why mathematically for this particular device, it's easiest to start with a column showing how far back we've stretched it, and then you can just calculate everything off of that starting position. Let's go ahead and fill out this work column. Work is taking energy away, so we have equal negative, and I'll do the friction coefficient, adding dollar signs to keep everything constant here. Mu times m times g times cosine. Make sure the angle is in radians. And the only thing I'm not adding dollar signs here is the distance to stretch the elastic back to. So no work if we don't stretch it back at all. And the farther we stretch it back, the more energy we lose from those frictional losses. Okay, so now we're on to the right-hand side of the equation. What potential energies are happening at the top? Well, we have some kind of an MGH at the top, so we can fill that guy in. We also have the spring is still a little bit stretched out at the top, so that's going to be an energy at the top too. So let's go ahead and fill in both of these potential energies from both MGH and from our 1/2 kx squared. So here is our MGH, so equals m times g, and our height here, if you look back, is 0.85 times sine of our angle up here. So I'm just going to add dollar signs to that. And this will be the same the whole way through. Our potential energy from the spring equals 2, because there's 2 sides of this. So we have 2 times 1/2 times k, and then our x squared is going to be equal to, since this is 0.5, then it's half of this, 0.25 minus the original stretch up here, and this is going to be squared. Okay, so don't forget to add your dollar signs into here. And this is going to be the same for all of them too, because we're starting off, we're going to release it from that top position for all of them. We now have all of our energies except for the kinetic energy at the top. So what we can do is by process of elimination, so here's all of our ones, our starting T1, V1, U1, and then at the end we have these two are our V2s. So our final kinetic energy, all we have to do is just say equals all of this stuff, T1 plus V1 plus V1, and then it's actually minus, but that column is already negative, so there's our work. And then we're going to subtract off. You can just use your arrow keys to grab those cells if it's giving you trouble, or you can type in the cells. So this is just finding the kinetic energy at the top. That gives us the velocity at the top, and we can use our constant acceleration projectile motion equations to then solve for where the target is. Okay, so here's our kinetic energy at the top. Why would the kinetic energy be negative here? So this is where we've just barely pulled it back. And if you think about what kind of gravity is doing, so you have to pull it back at least a little bit to get it to move. If it's not pulled back far enough, it's not going to move, is what that's telling us. Now that we have our kinetic energy at the top, we can use that to solve for our velocity. Now, if you have an arm swinging around, you'll have to take into account I omega squared in there too. For our situation, it's just 1/2 mv squared, so v equals square root of 2 times kinetic energy over m. So equals square root of 2 times our kinetic energy divided by our mass. Okay, so there's our velocity, and we can go ahead and split that velocity up into x and y components. It's negative here, so the top is going to be doing some funny things because we don't actually have a good velocity here yet, but we'll just ignore that for now. Okay, so the y component of the velocity, that's going to be equal to the overall velocity times sine of that angle. And for whatever device you have, you'll have to really study the geometry to figure out what angle this will be launched at. Okay, so Vx is equal to V times cosine of our angle. Don't forget the dollar signs in these guys. Okay, so we have the x and y components. And the next thing we want to do is figure out from our velocities what our target position is. And this is where I'm going to start by just defining a height. So if we're going from ground to ground, what I have in here is just 0.85 sine theta. So this is how far up off the ground it would launch just initially. And if we go from the top of the device down to ground, it would be negative 0.6. So what's the time that it would take for it to fall on the ground, right? So we can take the y velocity and this position and say, use the constant acceleration. So constant acceleration equation, plugging that into Mathematica, we're going to solve for the time it takes to hit the ground. We can then use the time to calculate what distance in the x direction it went. Okay, so again, our dy is just going to be equal to this guy right up here. I'm going to keep that constant, and we can always go back and change that if we're aiming for something at a different height. Okay, so there's our y position, and our time is going to be equal to, and this is using 9.81 meters per second squared kilograms and stuff. So we have equals 0.0203874.5. And then for every single Vy we have, we're going to plug in our Vy's. And this is quadratic formula. We want it positive times, so I'm going to do the plus version. Okay, so there's how many seconds it takes to fall. For the distance in the x direction, we're going to assume that velocity is constant. There's a little bit of air drag and stuff, but we're going to pretend like that's negligible. So our x position is just equal to our x velocity multiplied by the time it's in the air, which the time it's in the air is calculated by that height difference. Okay, so there is our dx, which means our total distance would be equal to square root of dx squared plus dy squared. So now we have something that we can graph out what target it will hit based on how far we've stretched our elastic back. Okay, so pulling up the graph here, you can just go to Insert, Scatter Plot, or there's one already set up for you. And what I have on here is the distance to stretch the elastic back to versus the distance to the target. So if you stretch your elastic back by 0.4, then you will hit a target right here, that is the distance to the target. And of course, if we come up here, and maybe our target is up above us instead of below us. So what happens if we change the y to the target to something like, I don't know, 0.5 meters up or something? So now we have a new curve, and we would have to actually pull it back a little bit to even get started here. So we can adjust our position to the target. We can go ahead and adjust our spring constant if we want to. So what if that was 50 instead of 40? How would that change our performance? Or if our curve is not matching what we actually get, we can come up here and change our friction coefficient. So if we need to grab a little bit more energy out of it, or if we need to give it a little bit less energy. So you can kind of mess around with these guys until you get your curves to match what you're experimentally measuring. Okay, hope that helps. Now this was just an example for this one scenario here. You're going to do something similar, but not exactly the same for whatever device you create. So whether it's stretched back bungee cords or springs or falling weights, start with the potential energy, calculate what kinetic energy it leaves your device with, and then it's just projectile motion from there on out. So that's a little bit from kind of everything that we've covered so far, if you can get through this. Okay, let me know if you have questions over this stuff.